Hello and welcome back to the unit review videos. Today we're going to review Unit 7, Transformations of Functions. This unit is going to be a general unit on what transformations are with functions. So this works with any type of function. Quadratics, linears, exponential, logarithmic, trigonometric, so forth. You get the idea. Square root. Okay. Any type of function it will work for. So some of the review videos we're going to look in the future, we're going to be applying these transformations. And also some of the review videos in the past implied transformations and some before, but we're really formalizing it in this unit. Okay. So here's what we're going to do. We're going to have one review video, because it's a fairly short unit. We're going to look at the general rules and how to transform a function, either given the notation that indicates the transformation or given two equations to find a series of transformations that goes from one function to another. And notice that we're dealing with vertical transformations and horizontal transformations. They're going to be separate because they're a little different from each other, but they're similar. Okay. And the types of transformations we're going to be dealing with, as we can see in the lesson overview, are translations, just going to be shifting them, reflections, and dilations. We're not worried about rotations because that's more of a pre-calc or a college level topic. Rotating functions. Okay, we're not going to worry about that. But we're going to finish out the review video also by looking at even versus odd. So take a look at the Common Core standards associated with this unit. So take a moment, read this, pause the video. Okay, notice this unit, this particular unit we're focusing on transformations, but this standard is going to apply to most of the future reviews as well, and some of the past ones. There are two formulas dealing with even and odd functions that you should know. Okay. We're going to get to the review later on in this video about how to tell if they're even or odd more specifically and how to apply these formulas, but in general, what you're going to do for testing even or odd, you evaluate the function at negative x. If you evaluate negative x and you get the exact same thing back, you can say your function is an even function. If you evaluate negative x and you get the negation back, you can say it's odd. Okay, so those are the formulas for even versus odd functions. Okay, so let's get into some reviews about the general rules for performing transformations. Now, order is going to matter, specifically if you are looking at an equation to find out what transformations took place. Now, if you look at PEMDAS, of course that applies to order of operations with expressions like adding, subtracting, multiplying, dividing, raising to exponents, and so forth. So it may seem weird to think about looking at these transformations in terms of PEMDAS. But if you look at PEMDAS, we deal with multiplication, division before we deal with addition and subtraction. So what that means, it implies, is that really you need to take care of dilations and reflections before you do transformations, because transformations deal with translations, not transformations. These are all transformations. Dilations and reflections must come first before you do any kind of translations. Dilations deals with multiplying, and so doesn't reflections. Reflections just deals with multiplying by negative. Okay, and transformations deal with adding. You could also think about it as multiply, divide, add, subtract. All right, but this is a good idea to think of when you are dealing with transformations with functions. Now, it doesn't mean you have to go in this order. You could do translations first. However, what that means is you have to probably do the opposite translation, because when you reflect it or dilate it, okay, it would go to a different location than where you want it to go to. So let's look at some specifics about vertical and horizontal transformations. When you're talking about vertical transformations, it's something that's happening to the function. Okay. That you're compared to. This is happening to the function, vertical transformations. Because if you think about function notation, f of x is really considered the y value. Okay, it's your vertical value, vertical direction. So whether you're stretching, reflecting, or translating, you're happening to the function itself. So we're going to be looking at just, if you're given a function f of x, what g of x does when it's transforming f of x is you're multiplying by a function and you're adding something to a function. So we're looking at this kind of transformation. When we look at horizontal, we're going to be dealing with what happens with the x's. But we're just going to worry about multiplying to the function, which is your a value, and adding to your function. Now notice, that function could be any kind of function. It could be quadratic, linear, and so forth. Okay. Now vertical stretch and compression, okay, that's when you're dealing with dilations. You're multiplying by a certain value. Now what you're going to do is you're going to look at your a value. Your a value is going to find out how you are stretching or compressing. If the a value, I'm going to take the opposite value just because I just want to look at the positive value of it. If your a value ends up being greater than 1, then you have a stretch. If your a value is less than 1, then you have a compression. Think about that for a second, right? If you have a function and you're multiplying a function by 2, you're getting larger by a factor of 2. If you're multiplying by 1/2, which is less than 1, you're getting smaller by a factor of 2. So it doesn't make sense to think about it in terms of a stretch in that case. It makes sense to think about it as a compression, a factor of 2, because you're getting smaller. I'm going to write some examples up here to illustrate each of these as we go along. So I'm going to consider the function f of x is equal to square root of x. We're looking at the square root function. Okay, that's a future review video, but we're going to look at what happens to that function. Okay, let's say g of x is going to be found by multiplying the function by 3, so 3 radical x, and then subtracting 2 from the function. Let's say that h of x, so we have two different functions here, is negative 1/4 of radical x, and we're adding 7. So in terms of stretches and compressions, g of x has a vertical stretch of factor 3. It's getting larger, so it's stretching. Okay, it's getting larger vertically by a factor of 3. H of x is being compressed by a factor of 1/4. By a factor of 4, should I say. So it's a vertical compression of 4. So notice that for stretch, it's going to be a stretch of factor A. If it's greater than 1, it's going to be a compression of factor 1/A. It's going to be the reciprocal. Compressions and stretches are reciprocals of each other. So if it's 1/4, you're being compressed by a factor of 4. It means you're dividing by 4. Reflections occur wherever your number you're multiplying the function by is negative, so it's less than 0. Okay, and vertical reflections are always going to be through the x-axis. Okay, so for the function g of x, we have no reflection because it's positive. But for h of x, we have negative 1/4 there, so it's a reflection through the x-axis. Lastly, our vertical shifts are going to be dealing with this d value up here. Okay, if your d is greater than 0, then you shift up d units. If it's less than 0 or negative, you shift down d units. So for g of x, it's going down 2. For h of x, it's going up 7. So some examples of vertical transformations, all combined into one place. Okay, take a moment to think about that. Write down anything you need to before going into horizontal transformations. All right, now let's look at horizontal transformations. Now, vertical transformations we're dealing with doing something to the function. Okay, horizontal, you're going to be doing something to the x values of the function. Think about that. It makes a little sense, right? If you're dealing with horizontal direction things, you're dealing with the x direction. You're doing things to the x values. Vertical, you're doing things to the function, the y values. Okay, because that's the vertical direction. Okay, so you're doing something to the x values. Now, with horizontal transformations, you have to think in terms of opposite. Okay. For vertical transformations, it was pretty much what it seemed like. If you were adding 7 to the function, you're going up 7. If you are multiplying by 2, you're getting larger by a factor of 2. Okay, but horizontal transformations are kind of backwards. So we're going to look at what's happening to the x values. So for g of x, we're going to be looking at what happens inside the function. Okay. Some b times x plus c. So let's first look at the two examples we're going to use. So let's say we use f of x is equal to, let's say, x squared. Let's look at the basic quadratic parent function. And let's say that we have the function f of negative 5x, and we also have the function, that's going to be g of x. And we also have h of x is going to be f of 1/2 x plus 4. Okay. So let's see what's happening with the horizontal stretch and compression. Okay. So the horizontal stretch and compression in terms of the function is always what you're multiplying the x by. Now, if you're multiplying by the x and also adding something, here's where you have to be a little careful. You always have to make sure you're multiplying by a binomial. Okay. You want to factor out what you're multiplying by, because that's going to indicate your horizontal shift in a moment. Okay. So horizontal stretch. Okay. If your b value is greater than 1, or it's positive, it's greater than 1. Okay, so like 2, 5, 7.3. You're actually going to have a compression of factor b. If you have a b value that is less than 1, you're going to have a stretch of factor b. Okay. So for g of x, I'm multiplying my x by negative 5. Don't worry about the negatives yet, just by 5. So this is going to be a compression of factor 5. Doing the opposite of what we think we're going to do. So this is multiplying by 5, we're going to divide by 5. It's compression of factor 5. For h of x, we're multiplying by 1/2. Oh, and I should change this too. Not factor of b for, but we're going to have 1 over b, just like what we had in the last one. Okay, my apologies. Okay. If we have h of x, we're multiplying by 1/2, so we have a horizontal stretch of factor 2. Horizontal stretch of factor 2. So horizontal stretch and compression is a little opposite what you think it's going to be. Okay. Luckily forever, on the flip side, is that horizontal reflections are not opposite. Okay, if you have a b value that is greater than 0 or known as positive, there's no reflection. If your b value that is less than 0, you reflect through the y-axis. So looking at our examples, okay, where we have a negative 5x, so we are going to be reflecting through the y-axis. But there's no negative in front of the 1/2 for h of x, so there's no reflection here. Now let's look at horizontal shift. Now those are going to be backwards, just like, or opposite, just like the stretch and compressions were. Okay. If your, so first notice before we talk about this, you have to factor out the stretch or compression factor first. Once you factor out the stretch or compression factor, then your C value, if your C value is greater than 0, or if it's positive, then you technically shift in the negative direction, which is to the left. If your C value is less than 0, then you shift right. Now, by the way, some teachers might have this formula up top rewritten as x minus c. If you see that, then it's just indicating to its opposite direction. Okay, but I'm using this plus c because when we look at the equations, we're going to be seeing the sign there, and we want to do the opposite, whatever the sign is there. Okay, so for instance, for g of x, we're not adding or subtracting anything to the negative 5x, so there's no horizontal shift. But if we're looking at h of x, it looks like we're adding 4, but remember, you have to factor out that 1/2. So really, I have h of x is equal to f of 1/2, and when you divide 4 by 1/2, you get plus 8. 8 times 1/2 gives you 4. So really it's not a shift to the left 4 because it's adding. It's going to be a shift to the left 8. Let me pause the video, think about that for a little bit before moving on to the next slide. Okay, so now we're ready to identify a series of transformations between two functions based upon horizontal and vertical transformations. Okay. So we're going to be given a function, let's say in general g of x, we have some function being multiplied by some a value, and you have b of x plus c plus d. So we're combining verticals and horizontal transformations. Okay, so let's start off with the function f of x equals x squared. Now I give you two functions, g of x and h of x, and we're going to describe the series of transformations that maps f onto g as well as f onto h. So remember, order matters. It's important to remember. Order matters, so that means we have to do, let's do the dilations, then we have to do reflections, then we have to do translations. Okay, order matters. Now just remember, dilations and reflections can go in any order that you want, but remember, this is what you do first, and this is what you do last. So for g of x, let's look in terms of vertical and horizontal. Okay, you're multiplying the function by -3 which means you have a vertical stretch of factor 3, and the negative means you have a vertical reflection through the x-axis. Okay, so there's the dilation and reflection vertically. Okay, now let's take care of the horizontal dilation and reflection as well. I'm not multiplying the x by anything other than 1, so it's not really getting larger or smaller. It's staying the exact same in the x values. And there's no negative in front of the x, so there's no horizontal dilations or reflections. So now let's look at the translations. The plus 8 is telling us that we're going up 8 units. And the plus 10 means that we're going to the left 10 units. Remember, if it's plus 10, that means we're going in the negative direction 10 units. Okay, so those are the series of transformations that map F onto G. So now let's look at h of x. For h of x, again, let's look at the dilations and reflections, and then we look at the translations. So I see I'm multiplying this x squared piece, this piece that's squared, by 1/2, so the function is being multiplied by 1/2. So that means I have a vertical compression of factor 2. Okay. There's no negative there in front of the 1/2, so we're not reflecting through any x-axis. Now let's look at the horizontal dilations and reflections. Okay. So I'm noticing I'm multiplying this x by a 4. So that means that I have a compression, a horizontal compression of factor 4. Okay, I have a horizontal compression of factor 4. I also notice I don't have any negatives there, so there's no reflections to the y-axis. Okay. Now let's look at the translations. Very clear, I'm seeing I'm going up 9. Okay, I'm going up 9 units from there. However, remember with the horizontal translations, I have to make sure I factor out that 4. So I'm going to rewrite this as 4, and take out a 4, I get minus 3. Okay, so there's my function with the factored out 4. That's indicating that I'm going to the right 3. Alright, pause the video now and get a sense for this before moving on. Alright, so let's do our final review by looking at even versus odd functions. Okay. So recall what I was saying on the very beginning of the formula slide, that if you plug in negative x into a function and you get the same thing back, that tells you you have an even function. Likewise, if you plug in negative x for odd and you get the negation back, you get an odd function. Okay. So let's look at some examples. Let's say I give you the function f of x is equal to 3x squared plus 4. F of x is equal to 3x squared plus 4. And I want to know, is that even or odd? So I'm going to test it. I'm going to plug in negative x and see what happens. Make sure you put it in parentheses. And if I were to do some work, square a negative number becomes positive, so 3x squared plus 4. Hey, look at that. Notice I get the exact same function back. So this right here is an example of an even function. Now one thing to note about even functions is that they are symmetrical with the y-axis. Meaning you can reflect to the y-axis and you get to a point on itself. Okay. So this graph of 3x squared plus 4 actually looks something like this. Okay. That's the graph. If you reflect this point over to here, it's reflecting. And if you look at the formula, f of negative x, here's x, here's negative x, it gave you the exact same output. Okay, so that's why when you plug in negative x, you get the same thing back. It's considered even, and why it's related to reflections to the y-axis. All right, let's look at another function. Let's say we had the function g of x is equal to 7x to the fifth minus 3x squared plus x. You want to say, is that even or odd? I meant to say x to the third. Write those exponents a little better. Okay. So plug in negative x. Okay. When you plug in negative x to the odd power, that means it changes the sign. So we get negative 7x to the fifth plus 3x cubed. Oh, actually, keeps the same sign, should I say. Keeps the same sign. So negative times negative is positive, and negative x. And notice I get the exact opposite of my original function. So if I factor out a negative, except if 5 doesn't become a 2, you get negative 7x to the fifth minus 3x cubed plus x, which is the same as negative f of x. That's telling me this is an odd function. And in terms of its graph, it's going to be symmetrical with the origin. Okay. So it's going to look something like this. Okay. I'm not sure if that's exactly what that graph looks like, but I'm guessing because it's the fifth power, and I know it's going to be symmetrical with the origin because it's odd, meaning that if I take a point right here, on the origin it's going to go to itself. A point down here will go up here. Or in other words, if I put in an x value and negate the x, I get the exact opposite y value. Okay. Now one thing that's really nice to point out here, look at the word even, look at the word odd, look at the exponents, okay, of the functions. Notice an even function will have even exponents, and an odd function will have only odd exponents when they're in polynomial form. It's a nice little thing to point out. Okay, of course, odd functions can't have a constant term. Okay, so a constant term really has x to the 0. So I guess you can consider that even though there's debate out there whether or not 0 is even or not. Right, pause the video, write down anything you need to before moving on. Okay, so here are the most important things you should take away from this particular unit. You should be able to examine an equation or graph of a function, determine how it was transformed from its parent function. So notice that applies to any type of function that you have. Okay, so this unit is going to be applied through future units. You should be able to sketch the graph of a function given the original graph and the transformation written in function notation. So whatever is happening to the points, make sure you multiply the points by such values, and I didn't really show examples of that, but you have examples in your notes about how to transform functions. You should be able to identify the graph of a function as either odd, even, or neither, okay, by examining its symmetry. So if you notice a reflection through the x-axis, through the y-axis, it's going to be even. If it's a reflection through the origin, then it's going to be odd. And if it's neither of those, then it's going to be neither. In algebraically determining if a function is even or odd or neither by plugging in negative x and seeing the effects of that, as well as sketching missing portions. And we didn't really do that in this review video, but if it says it's even and you see a graph like this, then you know it's going to be like that to finish it off. Okay, if you see a graph like this and you said it's odd, it's going to look like that in the rest of the graph. Okay. Alright, I hope this video will help you with your unit 7 review. I look forward to seeing you in the next video. Thank you for watching.